Okay, grade 12s. What we're looking at here is the physical properties of organic compounds. So what I've gotten here is a little summary of, in terms of your homologous series and understanding where each one fits in. So for example, if I have, what we want to do is understand exactly how intermolecular forces plays into organic chemistry. So if I have alkanes, alkenes, and alkynes, they're only going to experience London forces or London dispersion forces, or you can even call them induced dipole forces. These are the weakest intermolecular forces, and the least amount of energy is required to, and the word they're using here is break, and we know that what we don't want to use, let me say break, is the word that we want to use rather is overcome. So that's important. Right, then we've got, you've got the next thing, and like I said before, aldehydes and ketones are not actually part of the IEB, so we don't have to worry about them, but haloalkanes, you've got London dispersion forces, and you've got dipole-dipole forces. So the type of intermolecular forces that we consider as the most dominant force would be dipole-dipole. So yes, all of them experience London dispersion forces, but if they experience London dispersion forces and another type of intermolecular force, then we take the intermolecular force that is stronger. So that's your dipole-dipole force. These ones are stronger than London forces, but weaker than hydrogen bonds. More energy is required to, and again, we don't want to use the word break there. We want to use the word, we can scratch it out, and I want to use the word, overcome, rather, and I'll do the same here. Okay, so in essence then, we say that your dipole-dipole forces are stronger than London dispersion forces because they have, for example, if I look at a haloalkane, I'll give you an example. If I look at chloromethane, it's got hydrogens around it, but it's got a chlorine on this side. So when I'm looking at the actual molecule, I can see that on this side of the molecule, each of these hydrogens, when they're bonding with carbon, there's an unfair sharing. So the carbon kind of takes the electrons away, making this side of the molecule more delta positive. But on the other side, chlorine is more likely to gain electrons. So it kind of pulls that electron from that carbon unfairly, making this side delta negative. So that is how haloalkanes, like chloromethane or bromomethane or whatever the case is a dipole molecule. Okay, and then the last thing we have here is alcohols and carboxylic acids. They experience London dispersion forces, they experience dipole-dipole forces, and hydrogen bonds. But again, we're going to take what's the strongest one, and that's your hydrogen bonds. They are the strongest intermolecular force. The most amount of energy is used to overcome, like I said, these intermolecular forces. So that's just the basics of how they fit into it. But normally, it's simple. We look at a molecule, and once we make that decision, that's what it is. For example, if I have water, I know it's hydrogen bonding. It's dipole-dipole, but it's hydrogen bonding, and that's it. But when it comes to organic chemistry, we actually have to look further into the structure of each of these different types of molecules to find out where the intermolecular forces are. So the point of this video is to take as many notes as you can. The more information that you are willing to engage with and take the notes down and actually put it into your own handwriting and get it onto paper, the more likely it is to trigger a response from you when you're in an exam, and muscle memory and brain memory that you've done this before. So I know that it's going to sound repetitive. I know there's going to be notes that are recurring, but take down the notes. Make sure everything's in your books. Okay, so physical properties and intermolecular forces. We know that London dispersion forces are the weakest, followed by dipole-dipole forces, and then hydrogen bonding. Some terminology that we need to make sure that we understand for this section is we are looking at alkanes, alkenes, alkynes, carboxylic acids, alcohols, haloalkanes. But we have to talk about their physical properties. Now, the physical properties that we're going to focus on in this section are boiling point. So boiling point is the temperature at which the vapor pressure is equal to the atmospheric pressure, which is the external pressure. It is not the point at which a liquid starts to become a gas. We know that it is that, but that is not the official definition there. Then you've got melting point. Your melting point, these definitions, please make sure you write them down because you need to understand what's going on. The temperature at which the solid and liquid phase of a substance are in equilibrium. Then we've got a new term called vapor pressure. Now, vapor pressure is not part of the IAB, but we use it when it's like Vesper theory. Okay, it's a skill that you need to know that will be of assistance to you. Vapor pressure is a physical property that is useful to us. It is the pressure exerted by a vapor at equilibrium with its liquid phase of a substance are at equilibrium. So what that means is, if I look here at this diagram over here, if the atmosphere at room temperature, so if I'm looking at the first situation and I'm looking here at room temperature, at room temperature at 25 degrees, the atmospheric pressure is greater than the vapor pressure. Now, what starts to happen is you increase the temperature. So the temperature increases. And what happens is that the atmospheric pressure and the vapor pressure are now almost equal to each other. And when it reaches boiling point, which is at 100 degrees, boiling point, this is, we're looking at water, then the atmospheric pressure and the vapor pressure are equal to each other. So you can see that what we say is that the bubbles can form, the bubbles that form, they rise to the surface since the vapor pressure can overcome the atmospheric pressure. Right? So it looks at phase, we're looking basically at a phase change between liquid and gas. So draw a rough sketch of the diagram as we're going through here. Right, and then the last thing is viscosity. Viscosity is the property of a fluid to oppose the relative motion to adjacent layers. So basically what we're looking at for viscosity is, I'm just going to put it here on the side. We say it is the resistance of a fluid or gas to change in shape or movement. So basically we can say it is the opposition to flow. Okay, that's what viscosity is. So I know that vapor pressure and viscosity are new terms, right? So one of the things that we reiterate all the times is that we must remember this a little bit. Oops. We must say that compounds with higher boiling points will always have a lower vapor pressure. That's what we want to take out as our main point as we go through each of these. So you need to know what is boiling point, melting point, vapor pressure, and then obviously viscosity. Okay, so we start on physical properties. What we do need to note down is that physical properties of compounds depend on the strength of intermolecular forces, the IMF. The stronger the IMF results always in a higher boiling point, higher melting point, higher viscosity, but then a lower vapor pressure. Now, these physical properties, when it comes to organic molecules, so the physical properties of viscosity, boiling point, vapor pressure, melting point, are affected by the following four things. They're affected by intermolecular forces. They are affected by the number of types of functional groups. So now I'm looking at whether it's an OH functional group. I'm looking at if it's a COOH functional group. I'm looking if it's an alkane or an alkene. So I'm basing this on the functional groups. Then it looks at chain length, so that's your number of carbons. And the last thing, it looks at your branch chains, which are called your alkyl groups. So those are the four things that boiling point, vapor pressure, melting point are all dependent on. Please make sure that you are being proactive during this video. It is not just for you to just watch and browse over. I'm giving you solid, free marks for an exam. I'm giving you all the basis of how you're going to write out your answers in an exam. It is theory, but it also is very, very important for organic chemistry since it is a theory topic. All right, so we're going to look at each of the factors that affect these physical properties. Again, make sure you get this into your books. All right, so the first thing is intermolecular forces. Now, with intermolecular forces, you have weak intermolecular forces and strong intermolecular forces. So in comparison, obviously, to each other. So if I look at weak intermolecular forces, I'm looking at induced dipole forces and London dispersion forces. Now, alkanes, alkenes, and alkynes will experience a London dispersion forces or induced dipole forces. Haloalkanes and esters, they're going to experience dipole-dipole forces. So if I have weak intermolecular forces, then a small amount of energy is needed or required to weaken the intermolecular forces so that the molecules can move further apart. That means that we will have a low boiling point, a low melting point, and a low viscosity. Also, then a small amount of energy is then needed to change from liquid form to vapor form. So that phase change, which means you're going to have a high vapor pressure. It's more likely, so what we want to state here is that it is more likely to phase change in terms of vapor pressure. Okay, so that's what happens if you have weak intermolecular forces. So two things are affected. The boiling point and melting point and viscosity, they all will be a small amount of energy needed to get to low boiling point or low melting point, to their melting points and boiling points. In terms of vapor pressure, you only need a small amount of energy for that phase change, so the vapor pressure is then going to be higher. Now, remember, if you're comparing an alkane to a haloalkane, please remember that alkanes are experiencing induced dipole forces, but haloalkanes are experiencing dipole-dipole forces, so they will have the stronger intermolecular force between the two. Okay. Remember, you can always pause the video, take your notes down before you move on. All right, then when we come to stronger intermolecular forces are stuff like hydrogen bonding. Now, both alcohols and carboxylic acids experience hydrogen bonding because they both have the OH. The alcohol has the OH, but the carboxylic has the COOH, and it's this little OH here that we're looking at that gives us that hydrogen bonding. So a large amount of energy is needed to weaken the intermolecular forces to allow the molecules to move further apart. So when we ask you about intermolecular forces, these little statements that I'm writing down are the kind of things that need to be in the answers of your questions. Now, if you need a large amount of energy, so this is an exam response. Obviously, you're going to be a little bit more detailed. And please remember, IMF is not a valid acronym for your exams. You must write intermolecular forces. All right, if that happens, you're going to have a high melting point, high boiling point, high viscosity. That means that more energy is going to be needed to break out of liquid and vapor form. In other words, for that, just say here, for that phase change to take place. For that phase change, let me put it in another color for you. For that phase change to take place, you're going to need more energy. So when I say break, I don't mean breaking bonds or breaking intermolecular forces. I'm saying break out as in no longer be. So you're going to have a lower vapor pressure. So with these little bits of theory, I'm also going to give you some examples. For example, if we had to look at butane, just zoom into this a little bit. If I had to look at butane versus butanol, okay, butane still has 4 carbons in its chain. So this, remember, structural formula, condensed structural formula, semi-structural formula, molecular formula are all formulas that you need to make sure that you know. So I've got butane here. Oops. And on the other side, I've got butanol. And with butanol, instead of having a hydrogen, it's going to have an OH group attached to it. Now, when I'm looking at these two, the first thing I want to do in a test or an exam, if they're asking you to compare them in terms of intermolecular forces, you need to look at the structure. So I know that butane is an alkane. And alkanes only experience London dispersion forces or induced dipole forces. And but when I look at the butanol, I can see that the butanol has this OH. Now, if I have a bond of OH or anything to do with a hydrogen combining with an oxygen, a nitrogen, or fluorine, that tells me that I've got hydrogen bonding. So let's just put this here. The OL over here and this OH tell me that I have an alcohol. And alcohols experience hydrogen bonding. So between an alkane and an alcohol, it's very easy for me to see that which one has the stronger intermolecular force and which one has a weaker one. So in this statement, if they had to ask you about intermolecular forces in an exam, they're asking you to compare, you can say that both of them, both molecules have 4 carbons and 10 hydrogens. So that's the first statement, okay? The second statement that you need to write, I'm giving you your cheat answers, so make sure you memorize the order. The second thing that you need to mention is what they are. So you can say that butane, oops, I don't know why it keeps doing that. You can say that butane is an alkane, which is a nonpolar molecule, and can only experience London dispersion forces, whereas, so your next statement, whereas butanol is an alcohol and is a polar molecule with a hydrogen to oxygen bond and is therefore experiencing hydrogen bonding. Okay, so now you've discussed both molecules. Your final statement must say, therefore, butanol will have a stronger intermolecular forces when compared to butane. That is what that answer should look like. It's a 5-mark question, 4-mark question. You make sure you identify how are they similar. You then discuss each molecule in terms of 2 things. Their polarity. You must discuss their intermolecular forces in detail. And the last thing, you must conclude. Answer the question that they're asking you. So this works is if I have something like butane, which is a weak intermolecular force, compared to butanol, which has a strong intermolecular force. But what happens if they ask you to compare an alcohol to a carboxylic acid, or an alkane to an alkene? So I'm going to show you that example next. So please make sure that when you're answering these questions, the best thing to do is, the first thing when they ask you the question is to draw. Always draw out structural formula. Once that's done, it helps you to easily see. Having the molecular formula doesn't help anything. Okay? Draw the structural formula so you're in a place where you can see exactly what is going on inside the molecules. After that, and you've identified everything and you're sure, then you go into writing out your full statement of what needs to be there. I can tell you now, you will get 5 full marks if you answer your questions like this. Okay, if I look at this example over here, and what we're looking at is methanol and methanoic acid. Now, both of them form part of the strong intermolecular forces. Now, how does this whole thing work? So the first thing you need to understand is where the solid lines are. Here, you have a covalent bond. So that's not what we're looking at. So we're not looking at this covalent bond that's taking place. What we want to look at is what's happening between the molecules. So it's an intermolecular force. So for example, if I'm looking at methanol, I can see that wherever I have a hydrogen, that hydrogen can connect to, and I use a dotted line, to an oxygen. So if I have another hydrogen on the same on the molecule, it connects to the oxygen. And that connection that you have here, that is your hydrogen bond. That's the hydrogen bond, which is an intermolecular force. Okay? Now, what I can see here is that at any given point per molecule, okay, if I'm looking at each molecule, at any given point, one hydrogen can meet one oxygen. That's what we're looking at. Okay? Now, if I go to the carboxylic acid, methanoic acid, I can have a look that this oxygen can connect to that hydrogen, or I can put it in a way that makes better sense. I can say that this oxygen can connect to this hydrogen, and this hydrogen can connect to this oxygen. So now, my situation here is that methanol is experiencing hydrogen bonding. Okay? Methanoic acid also is experiencing a hydrogen bond. So both of them are experiencing hydrogen bonding. Now, if we had to ask you in an exam, which one is stronger, you've got to look a little bit more deeper. So when I'm looking at these two molecules, if I look at methanol, I can see that the hydrogen bond, there's only one site for hydrogen bonding. But when I'm looking at methanoic acid, there are two sites for hydrogen bonding. Now, in this situation, you need to actually answer the question. So the first thing we want to do is make sure that we state what's happening. So you'll first say that methanol, so the first statement, methanol and methanoic acid are polar molecules. Look at that spelling. Polar molecules which both experience hydrogen bonding. However, methanol is an alcohol which you have to mention and only has one OH functional group. While methanoic acid has two oxygens and is a carboxylic acid with a COOH functional group. So there's some of your marks. Then the last thing you need to state, last point you need to state is that methanol only has one site for hydrogen bonding, while methanoic acid has two sites for hydrogen bonding. I want you to have a look at how I'm answering these questions, because I want you to understand that when you use the word it and them, that's not specific. You must mention what you're talking about. Don't say it has only one site for hydrogen bonding while the other one has two sites for hydrogen bonding. No. You must mention specifically. If you use the word it, I cannot give you the mark. So take the effort and the time into answering these questions properly. And your last thing you need is a statement. And you will say, therefore, methanoic acid has stronger intermolecular forces. Again, no IMF. Sorry about my spelling there. Intermolecular forces when compared to methanol. So what you want there is to have a final statement at the end. So this is what your answer looks like for if they had to ask you to compare the intermolecular forces of two of the stronger molecules that you get. All right, the next thing we're looking at is the number and type of functional group. So alkenes, alkenes, and alkynes, they experience London dispersion forces. Haloalkanes, which are called alkyl halides, experience dipole-dipole forces, and they are stronger than London dispersion forces. So alkanes, alkenes, and alkynes, as well as the haloalkanes, remember when they compare to each other, the haloalkanes are stronger than the London dispersion forces, but when compared to alcohols and carboxylic acids they're weaker. So less energy to weaken the intermolecular forces, which will result in low melting points, boiling points, and a low viscosity. Also, less energy will be needed for the molecules to evaporate, so you're going to have a high vapor pressure. So that is depending on the functional groups. If I look at the different types of functional groups, it tells me if it falls under weak intermolecular forces, or if it has lower melting, boiling, and viscosity properties, or it has higher vapor pressure. Then when you get to the alcohols and carboxylic acids, the more energy needed to overcome the intermolecular forces, it's going to have a higher melting point, higher boiling point, and a higher viscosity. And when it comes to vapor pressure, more energy required for molecules to go through evaporation, so the vapor pressure is going to be lower. So those are your functional groups in terms of how they affect your factors of boiling point, melting point, viscosity, and vapor pressure. So a blanket statement that we can write down is that increasing the polarity of a functional group will increase the intermolecular forces. It will increase the strength. Increasing the polarity of a functional group will increase the strength of the intermolecular forces, which will increase the boiling point, melting point, and viscosity, but will decrease the vapor pressure. Alright, so if I had to look at these three examples here, and what I've got is pentane, I've got pentanoic acid, and pentanol. Okay. Now, if I'm looking at these three, my molar mass for pentane is 72 grams per mole. My molar mass for pentanoic acid is 102.13 grams per mole. And my molar mass for pentan-1-ol is 100 the molar mass here is 88.15 grams per mole. Okay, so I can see they're changing molar masses. But if I have a look at my boiling points, the boiling point here for pentane is 36 degrees Celsius. That's just a basic. So I have an alkane, I have a carboxylic acid. Remember, you got to know all of these formulas. So structural formula, semi-structural, condensed structural, and so on. My boiling point, however, if the functional group then changes for pentanoic acid, it increases. So I've got 186 degrees Celsius. And my boiling point then for pentanol, pentan-1-ol is 138 degrees Celsius. So what you can have a look here is that, yes, carboxylic acids and alcohols have hydrogen bonds. Okay. Yes, they both have 5 carbons. Here you only have London dispersion forces. Yes, they only have, they have the same amount of carbons, the pent, right? But look at the molar masses and then look at the boiling points. So even if I have 2 molecules that are exactly the same, like a carboxylic acid and an alcohol, which have hydrogen bonds, I also have to take their functional groups into consideration. So I can see that, yes, they both experience hydrogen bonds, but because of their functional groups, which comes from here and here, we can then see that their boiling points are significantly different based on also molar mass. So that's also a deciding factor as to which one will have a stronger intermolecular force. Alright, the next thing that we're looking at is chain length. Increasing the chain length will increase the number of carbons, which will then increase the surface area, and there will be an increase in molecular mass. So what we want to pull from there and make sure that we understand each of those is when we have the chain length being increased. So if the chain length increases, then we're going to have, and I'm just going to use another color, we're going to increase the number of carbons, we're going to increase the surface area, and increase the molecular mass. Those things have to be mentioned in your answers. So intermolecular forces increase with an increase in molecular mass and change length. So I'm going to give, the bigger the molecule is, the stronger the intermolecular force. So bigger molecules will result in stronger intermolecular forces. Right, which means, therefore, more energy is required to overcome the intermolecular forces. The boiling point and melting point from methane to octane is going to increase. The vapor pressure will decrease if there is an increase in molecular mass or chain length or number of carbons. So the vapor pressure will increase from octane to methane. Like I said, what's happening with the melting points, boiling points, and viscosity, if they're increasing, the vapor pressure has to do the opposite. So if the boiling point and melting point increase from methane to octane, then vapor pressure must increase from octane to methane, from the biggest molecule to the smallest molecule. And our blanket statement that we can write is, increasing the chain length increases the surface area and increases the strength of the intermolecular forces. Therefore, an increase in boiling point and melting point and viscosity while decreasing the vapor pressure. So if I had to look quickly at these examples I've got here, these are all alkanes, right? So I've got here propane, butane, and I've got pentane. Okay. If you look at the number of carbons, it's increasing. So here I have my carbon number is 3, here my carbon number is 4, and here my carbon number is 5. If I had to look at their molar masses, we can see there's an increase in molar mass because I've got 44 grams per mole here. I've got the molar mass of butane at 58 grams per mole. And my molar mass for pentane is 72 grams per mole. So if I had that as my value, I can see that if I increase the carbon numbers or I increase the length of the chain, because you can see it's getting longer as well, my molar mass increases. Even though I only have London forces, the boiling points are affected as well. So if I look at the boiling point of propane, it's negative 42 degrees Celsius. If I look at the boiling point of butane, it's negative 0.5 degrees Celsius. But if I look at the boiling point of pentane, look at how drastic it changes. Even though it's 3.5, the boiling point increases drastically. So in these three, they're all alkanes, that's fine. Their carbon numbers are increasing, their molar masses are increasing. With the increase in molar mass, chain length, and number of carbons, I can see that the boiling points increase as the chain length, molar mass, or number of carbons changes. So even though they all are experiencing London dispersion forces, which is quite the smallest or the weakest intermolecular force, even though they're all experiencing that weak intermolecular force, depending on the carbon numbers, length of the chain, or molar mass, we can see that the boiling point increases if any of those three things increases. Okay, the last thing we're looking at is branched chains. Now, when we talk about branched chains, we're talking about the alkyl groups, right, which means they attach themselves to the actual main chain. Now, molecules where carbon chains are branched have weaker intermolecular forces, so less energy is required to overcome the intermolecular forces. So you're going to get lower boiling points and melting points and a lower viscosity, which means there's less energy needed for evaporation or phase change, which means the vapor pressure is going to be much higher. All right, molecules that have straight carbon chains have strong intermolecular forces, so more energy is required to overcome the intermolecular forces. So you're going to get higher boiling points and melting points and a higher viscosity. Whereas here, more energy is going to be required for phase change, and there will be a lower vapor pressure. But obviously, it's not just as basic as this. I'm going to show you some examples of how that works. So if we look at our ideas generally, we can say one of two things. Decreasing branching, so less branching, increases the surface area and increases the strength of the intermolecular forces, which increases the boiling point and melting point, but will decrease the vapor pressure. Increasing the branching decreases the surface area and decreases the strength of the intermolecular forces, which decreases the boiling point and melting point, but will increase the vapor pressure. So you can write it either way. So I'm just going to show you some examples of how this actually works. So if, for example, I had 3 structural isomers, what you'll notice about the structural isomers is that they have the same molecular formula but different structures. So now if I'm looking here at these 3, they all have the same molecular formula, but their structures are different. So how are they different? They've all got 5 carbons. But if I look here at the first one's pentane, then you've got 2 methyl butane, which tells me here is my branch that's coming off my second carbon. So 2 for the second carbon. Methyl tells me there's 1 branch coming off of it, and it's got 4 carbons in its main chain, so butane. Then I've got 2,2-dimethyl propane, so my main carbon chain is 3 carbons, but on the second carbon I've got a methyl at the bottom and a methyl at the top. So 2,2 shows me that on the second carbon twice I've got 2 methyl groups. So what we can notice is that as I'm going from pentane to 2,2-dimethyl propane, as I'm going across between the two, my branching is increasing. So branching increases. Okay, so what does that mean for us? Okay, so if I'm looking at the branching increasing, I can say that the first point I can say is that the intermolecular forces from pentane to 2,2-dimethyl propane decreases because there's more branching. Okay, so I can say that also, if I look back at my main statement here, we are increasing the branching. So the intermolecular forces get less. The surface area, decreases. And we know, like I said, it's linked to chain length as well. We can also say that intermolecular forces decrease with increases in branching. We can say that the weaker the intermolecular forces are, less amount of energy is required to overcome the IMF. So therefore, the boiling point and melting point and viscosity decrease. We can also say here that the vapor pressure increases with an increase in branching. We can even say, which is important to us, it increases because there is a decrease in surface area. So we can see that it is similar to when we talked about chain length. So we can say that, we can make two other statements. We can say that therefore, the boiling point of a straight chain is higher than that of its branched isomer. Okay, and we can say that the vapor pressure of a straight chain isomer is lower than that of its branch chain. But like I said, all of this information is theory. That's why I said take notes. Even if you put it in your study notes, get it in your book. You've got to memorize all of this. It is all rote learning. It's understanding the background of organic molecules and intermolecular forces that can help you get through any sort of assessment or test that has organic chemistry. These notes, I cannot stress how important it is or how necessary it is for you to make sure that you've taken things down, you read over it, reread over it. There's no time to watch these videos twice. So if you put the effort in, I can tell you at the end of the day, it's going to pay off. Right, and that's the end of intermolecular forces and organic